All right, so this is part 4 of the video series on chair conformations. In the previous video, we talked about how to draw out chair conformations, and now we're going to go through how do we determine which one of the two is the most stable one, or in other words, which one is the lowest energy. So whenever we think about most stable, we should always be thinking about lower energy. So to determine which one is the most stable, we have to determine which one minimizes the unfavorable diaxial interactions. And so diaxial interactions occur between axial groups. So for example, here in the structure, we have two axial groups that are spaced 2 carbons apart. So we know that carbons or the axial groups alternate facing up or down. And so the ones that are 2 carbons apart are going to be facing the same direction. So we can see that both of these are facing up. And so this is called a diaxial interaction, which is unfavorable and is due to steric strain between those 2 methyl groups being aligned with each other. We actually also get diaxial interactions between those 2 methyl groups in this hydrogen right here that's on this carbon. And that diaxial interaction is not as bad as 2 methyl groups since a hydrogen is smaller than a methyl group, but we still do get diaxial interactions between that methyl group and that hydrogen here, and this hydrogen and this methyl group in the top right. And if we were to draw in the hydrogens that face downwards on the axial groups, we actually also get diaxial interactions between this all of those axial groups. And those are also unfavorable. However, hydrogens are smaller, and so they aren't as bad or destabilizing as some of those bigger methyl groups are. If we take a look at the structure on the right, here we can see that those 2 original axial groups are now in the equatorial positions. And so these methyl groups don't experience diaxial interactions, and so they're not destabilizing in this position. We do still get diaxial interactions between the hydrogens that are on those methyl groups. So this are on that same carbon as those methyl groups. And so these 2 hydrogens right here are spaced 2 carbons apart. And so we still get diaxial interactions there. However, hydrogens are pretty small, so they're not really, that steric strain isn't really going to be that high, and so it's not that bad. And so if we think about minimizing the diaxial interactions, we want to minimize the amount of large groups that are placed into an axial position. And so for this structure here, where we have 2 structures or 2 methyl groups in axial position on the left versus none on the right, we know that that's going to be bad. And so it's going to be less stable, or in other words, higher energy. And so what that means for the equilibrium is that instead of having this equally spaced arrows where we have, or where that would indicate that we're approximately 50-50%, instead what we end up having is that the structures heavily favor this right structure here. And we have some proportion still in that left state, and but the overall equilibrium favors the structure on the right. And so again, this one on the right is going to be more stable, which is the same thing as saying lower energy. And on homework assignments, I'd really recommend kind of keeping track of whether they're asking which one's more stable or which one's higher energy, because those are like flipped, the meaning is flipped for those. So just be careful with like what they're asking, or if they're asking for like the dominant state. So the more stable, lower energy is also the dominant state. All right, so yeah, so altogether, we're just trying to identify which structure has the fewest number of groups within the axial position, or the biggest groups. All right, so let's take a look at this practice problem right here. So these are the structures that we drew out in the previous question. And so now we want to go through and identify which groups we have in the axial positions, which are going to be that chlorine and the bromine in the first structure. And then that OH, only that OH in that second one. All right. And so sometimes questions ask you to identify the types of destabilizing interactions that structure would have. And so let's go through the types of diaxial interactions that these two structures have. So in that first one, we have that chlorine interacts with the hydrogen from 2 carbons away on both sides of the ring. So I drew in all the hydrogens that it would have interactions with. So it has 2 types of interactions here. And note that the bromine and the chlorine do not directly clash with each other. That's not the main problem within the structure. Because that bromine interacts with the hydrogens that are also 2 carbons away. And so I'll highlight those in purple right now, but we can see that there's this hydrogen pointed down and this hydrogen pointed down. And so those are the diaxial interactions that bromine has. And so altogether, this structure on the left has hydrogen bromine diaxial interactions, and specifically has 2 of them. And then it also has hydrogen chlorine diaxial interactions. And in comparison to that, we can take a look at the structure on the right. And so here we have only that OH in that axial position. And so we can draw in those 2 hydrogen, or we already have one drawn in, but we can draw in and highlight those 2 other hydrogens that also have an axial position 2 carbons away. And again, note that where the axial interactions occur between axial groups that are facing the same direction. So all those green groups are facing up, and the purple ones on the left are facing down. And so on the right structure, we only have HOH diaxial interactions. And so altogether, we can see that we have a lot more diaxial interactions on the left structure. And even though an OH group is slightly bigger than a bromine or chlorine, that size difference doesn't outcompete the fact that we have 2 versus 1. And so when we think about the equilibrium, we know that the structure on the right is going to be more stable than the one on the left. So we can redraw our equilibrium arrows to be longer pointed to the right. And again, that's only because we have 1 diaxial. So it's more stable and lower energy than the one on the left. And so at equilibrium, a larger percentage of the molecules will be spending their time within this state. And to be clear, the structures are constantly alternating or like flipping back and forth. It's just like if we were to take a snapshot, where would those molecules be? It doesn't mean that they're locked into that state. All right, so altogether, to determine which one's the most stable, you would first just identify which diaxial interactions you have and then minimize them and choose a structure that minimizes them. However, there is a few key groups to pay attention to, and here I labeled them as notable groups. And so these are going to be groups that are very, very large. And so, for example, a tert-butyl group and an iso-propyl group are very, very big. And so the interactions that we get with those groups are going to be so destabilizing that they're going to heavily favor one of the chair conformations, regardless of which groups you have, other groups you have on the ring. So let's just draw out a tert-butyl, and another word for a tert-butyl is a T-butyl. So you might see it in that way within your assignments. I was there for a second. All right, so a T-butyl group looks like this, just looks like kind of like a chicken hand almost. And then an isopropyl group or an I-pro group, which you might see just has 2 methyl groups. And so we can imagine that each of those carbons or methyl groups has those like 3 hydrogens at the tips. And so there's a lot of bulk or a lot of kind of think of it like branches, like they're very big groups that cause a lot of steric strain. All right, so let's draw in using these chairs. Here we can draw in a T-butyl group here in the equatorial position on that first chair. And so when we do that chair flip, actually, I'm going to draw that of this carbon right here. Let's draw the equatorial group on that carbon. So if we draw it here, We start off with the equatorial position, and when we do the chair flip, it ends up being axial on this top carbon right here. And so in this state, this tert-butyl H in this H form those diaxial interactions. And tert-butyl H interactions are so destabilizing that they lock in the chair into the other conformer to avoid those interactions. And in other words, this is also going to be the chair in which that tert-butyl group is in the equatorial position. And so we would want to choose this chair where this group is in the equatorial position as the most stable one. And equilibrium heavily, heavily, heavily favors that left side. And so this is very important for when you consider some reactions within like advanced or more advanced sections of predicting products of reactions, where you would have to consider the positioning of a group like that to determine if like another group is available for a reaction. All right, and so I'm just going to cross out these just to kind of emphasize that we don't want those interactions. And one thing to note is that even if we have, let's say that we add in some other groups, and so I'm just going to copy this and draw another potential option. Now, let's say that we have, in addition to those same equatorial groups, let's add in some other groups that would also be, or would be axial in these other structures. So let's draw in like a methyl group here, and then we can draw in like a chlorine group here, which would become equatorial in that second position. So let's say that we have this structure here, where now we have diaxial interactions for this methyl group and this chlorine right here. This would not change how favored the equilibrium is. Or it would slightly alter it, but regardless of the fact that we now have two groups that would be experiencing diaxial interactions in that left structure, equilibrium would still favor the one where you're not placing this big group in the axial position. And altogether, you would still want to choose this structure as the main one, or the one that's favored at equilibrium. All right, so that wraps up this video. If you haven't already done so, I recommend going through those chair confirmation practice problems. And then I will post those notes to be available as a PDF in the Google Drive folder for organic chemistry.